and welcome to PyCon ID session 2. Wait a minute, seems like my camera is not really good. Okay, it's all right. Okay, so in this session, we will have Neeraj Pandey. He is a senior at Asoka University, and over the years, he was worked on a variety of Vertex software and data science application, as well as computational arts and quantitative finance projects, and likes the challenge of creating new tools and applications. And then Neeraj, in this session, will deliver a talk with the title "The Joy of Creating Art with Code." So what the talk is about? So we will learn about how the computational, psychological, psychological, and economic aspect of AI generated art, music, and generative design, along with automatic computational tasks using machine learning and artificial intelligence. So art is everywhere. It's beautiful. So unleash the creative artist inside of you with the beautiful of generative art. So let's invite Niraj to the stage. Hello, Neeraj.
Hello,
Hi. How are you?
doing good. How you doing?
Yeah, good. I'm good too. So, is this your first PyCon or you have talked into several PyCons before?
Oh, this is like my fifth PyCon now.
Oh, the fifth PyCon. So, since what year? Since when have you tried
20,
to 20?
2019.
Oh, 2019. It's your first PyCon, right?
Exactly,
Right.
yeah.
Where is it? Where is it?
It was PyCon France.
France. So, do you live in France right now?
No, I'm in India.
Oh, you are in India, but you are attending PyCon France, right?
Yeah, right.
Okay, okay. I think uh I'm 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 really interested about the talks because when we are talking about creating art with code, sometimes what I think is just using Turtle Python and then create the a line with with some code and then create line and then you generate some image. Sometimes we use it as for fun, but for these talks, I think the art is like more complicated or anything. So, uh, if you are the watcher, the attendees is really interested about this talk, so I'm gonna go to Neeraj. I will share your screen, and then the stage is yours. Thank you.
Perfect. Thank you so much. So, welcome to PyCon Indonesia. This is the joy of creating art with code. Before we proceed, I'm Neeraj. I'm currently a senior student at Ashoka University. My area of interest lies in computational arts, quantitative finance, and full stack data and web applications. So the main goal of this talk is to look at Python as an artistic or visual programming language with the simplicity and um, beauty of generative art. So the points for discussions are like what is generative art, a little history about how creative systems work, and history about generative art. Then we'll be going about processing.py, which is a library for creating these artistic tools, and we'll be seeing examples using geometry, algorithms, and randomness, and few more examples in pixel sorting and all. So any art which is created through the use of an autonomous system can be classified as generative art. It uses iterative commands to draw vector-based shapes to the screen, and most of the art in like created classified as generative art draws inspiration from the modern art, especially the pop art. And whenever we are working on generative art, an autonomous system is usually required. Otherwise, the outcome will be mostly classified as digital art. And randomness could be one sort of an autonomous system here. So whenever we work about generative art, people usually ask, is it being creative or not? So we have to understand what exactly creativity is all about. So Michael D'Angelo said, I saw an angel in the marble and carved until I set him free. So thinking, investigating, learning, discovering new ideas, and tackling problems while taking chances all forms together a creative person. And it entails no capacity to think independently of any one line thought in order to seek the chances knowledge and transforms one inner cacophony and a riot of sensations to neural transformation, and they together connect to being creative. And when we talk about the traditional definitions of being creative, it's something which is related to religion and something which has religious beliefs. But like since the industrial revolution, it using paint and was more easily accessible to people, and artists came up uh, in the modern world with the coming of these museums. Artists start signing their art pieces with their own styles, and whenever we're talking about a creative product, we're talking about something which is novel and has some value. Although novelty is frequently used as a distinguishing characteristic of a creative production, but value is also required in doing so. And it's easy to envision that it's uh, easy that something that has never been produced before, but it's also should have some sort of value. And this brings us to something called a Dada movement. So in 1916, the Dadaist movement advocated in favor of this because previously it was meant like art has to be something until the limits of what is described as art. And we saw like toilet seats have been classified as pieces of art. But the critics argue that the art journey we take is has the ultimate meaning, and this ultimate meaning has something in the act of doing. But on the other hand, people used to think that art is something important in the world, and as a counter argument, there is a widespread belief that everything labeled art is deemed art. This is because, like, once the mind is educated about something is termed art, we tend to view it such. And this is something art historian E.H. Gombrich once said, that art with a capital A. And as a result, the Dada movement arose, which questioned establishment notions of art, for which it was also known as the anti-art movement. And it has a huge impact on the general public attitude. And the Dada movement is spirit blossomed in the 1960s and 1970s when it went into the video games and then to the computational arts. And in 1970s, we saw the emergence of generative art, generative music, and all other kinds of expression, which paved their way to the 21st century. And the Dada presented a new perspective that was less about aesthetics and more about meaning and context. So this brings us to about what exactly was generative art and how it was started. So in analog art, which is the art which is like manipulated by hand, complexity and scale requires exponentially more effort and time. And what we see is like computers excel at repeating processes near endlessly without being exhausted. So as we will see, like the ease which with computers can generate complex images contributes greatly to the aesthetic of generative art. And this is one of the best known pieces of generative art called Scotter by George Nice. And Scotter starts with a standard row of 12 squares and gradually increases in magnitude of randomness and rotation and everything once we move from top to the bottom. But like if you imagine for a second, like you have to create such an image using a pen and piece of paper, it seems easy, but the only problem is like it's going to take hours to complete. But like on the other hand, if you give the same iterative commands to the computer and like let it run for some time, you're going to generate thousands of similar art pieces in a fraction of minutes. So before we proceed, we'll be using processing, and processing is uh, a library created for this artistic environment, and it has been created in the media arts to like keeping in media arts in mind, and it's intended to educate the fundamentals of computer programming while simultaneously functioning as a software sketchbook for a variety of media arts students ranging from designers, artists, architect in their prototyping and production. And processing is available in different modes in Java, Python, Android, and JavaScript. And the example we'll be seeing will all be in processing.py mode. So it's a good practice to like quickly go through the functions and see how they work. And so basically there are two functions. One is the setup and one is the draw. And setup is the function which runs when the program is executed. And it's mostly used for the initializations of methods like height, background, noise details, blur, and other features. And draw is a function which runs endlessly unless we ask to stop. So it runs in loop, and each statement is executed in sequence, and after the last line is executed and the first line is executed again. Okay, so yeah, so the output for the last slide will be a circle on a black canvas. And if we see all these art pieces, so this was an art pieces called Cityscapes. This uses blur effects and noise patterns. So we will be seeing like mathematical functions like noise, trigonometry, shadows, another filter techniques like blur, and algorithms like Poisson, dissampling, pixel sorting, L systems have been majoritarily used in these art pieces. So in the next slides, we'll be going over to a few of them and see how they combine to making simple art forms. So as we discussed, an autonomous system is usually required, and random is one of that autonomous system. So this is like one of the most important function that is being used in generative art. And random function differs in different programming language, but the main objective here is to like provide a random floating point number between 0 and 1. And if you just like plot a series of random numbers, you will see this like very uneven graph. And even if you like try to interpolate them, you will see that there is no relationship between the last number generated and the next number generated. So the initialization of a random is like pretty straightforward in Python. It's like you just like say random, and it's gonna just like give you a random floating point between 0 and 1. You can just like provide your range between min and max, and you can just like create a random number between 0 and the number exclusive. And before we look at some proper art forms, we have to understand how an artist canvas works like. So uh, we have vector operations like shapes and other methods happening all around. So we need to understand this canvas. And as a result, this canvas is usually a 2D Cartesian plane with each point representing a vector in a 2D space. So we have this Cartesian plane on the right hand side where each point is represented by x and y coordinates, and has the capital X and Y has the instructions to go from the origin to that point. And we can further use like scaling, transformation, and the other linear algebra operations to process these forms. And this is like how we can create a single point in line. So a point can be initialized by just like specifying the x and y coordinate, which will be drawing a point at the coordinate in space. And you can just like also create a line by providing the point coordinates of 2 points, x1, y1, x2, y2. You can also update the color of the stroke by providing the hex code. And you can also work around the thickness of the line you're creating by using stroke weight. Similarly, if you're working on PyCairo, you can use the context library, and just it works in a similar way. You can create a line by using line2 and a stroke by dot stroke. And these pieces of art are created using varying thickness and intensities of lines and dots. On the left hand side, there are vertical lines of varied lengths, as well as in they are being positioned randomly. On the right hand side, there is like large palette of colors which I've used to like use as a stroke at random, and lines of varying length which are created using those color fills. So we'll be seeing like how these very few lines of code can generate some varying iterations when working with generative art. And okay, so yeah. So the other important function is a curve vertex and the Bezier curves. So curve vertex is it basically specifies the vertex coordinates for the curves, and it's an implementation of Catmull-Rom spline, which is a form of interpolating spline that is basically a curve goes through the points, and it gives the vertex coordinates for curves in processing. And it's kind of similar how you work with vectors in your digital tools like Illustrator and all. Similarly, you have Bezier curves, which is again a vector graphics tool, and it's a flexible mathematical curve which is defined by anchor points and control points. So they are basically the vector points again, which you usually see in all these digital tools like Illustrator. And if you have to see like how we use those functions, we have a Bezier function in processing, which requires 3 points, and which are the initial points, the final points, and the anchor points. This will be creating a Bezier curve on those specific points. And so if you see this GIF, here I'm creating a Bezier curve to the canvas whose endpoints are being controlled according to the noise value. So to draw it, we start with a for loop from 0 to 4 because we're using 4 points here, and generates this will be generating 4 points in a single frame. As we see, we have initialized the x and y arrays as an empty one, which are then subjected to noise in line numbers 17 and 18. And noise is like introducing randomness to something, but it's smooth. It has a smoother shift between values than the random function. And once we get the x and y values, we'll be incrementing those m and n factors, which will be utilized further to update the noise values in the next iteration. And once we have exited the loop, we will use those four values generated inside the loop, and we'll be putting them as a passing them as a parameter to the Bezier function. And as we are not like using a no loop, so it will be iteratively running again and again. And after like a few iterations, you will see that the outcome will be something similar to numerous numbers of curves. And the other function is the curve vertex, which is as similarly as seen before. Then we can simply create a curve vertex by passing the x and y parameters. And we can use the curve vertex to create them scribble like art form, like I'm using it over here. And to create a little curve between the second and third points, you need at least 4 points, so that one is the anchor point. And using a fifth point can then create a curve between the second, third, and fourth point. So in this canvas, we are traveling from top left to the bottom right of the canvas. And on line number 13, we are taking the curve vertex, which is like the I, which is taking the ith and the jth index of the loop and adding a random number between -10 and 10, so that there is some sort of randomness include. And we will get a single point on the canvas if you use a single curve vertex. As a result, we'll be adding a bunch of curve vertices. So as we can see, we have added 6 curve vertices over here, and this will generate a scribble type effect as we saw in the last slide. And the outcome is like we are incrementing by 40 and 30 pixels, so we have space in between, and each output is literally different from each other. And we can also work around simple shapes, like you can create an ellipse by passing a, b, c, and d parameters, where a and b are the x and y coordinates, and c being the width and d being the height. Similarly, you can create a rectangle by passing the x coordinate being the a, the y coordinate, the width of the rectangle being c, the height of the rectangle being d. You can also just like add some radius on the borders by TL, TR, BR, BL, which are the top left, top right, and bottom left corner radius. Similarly, if you're working with PyCairo, you can simply call context of rectangle, passing the same parameters, and you will be able to create a rectangle. And these are the experiments based on the composition 2 in red, blue, and yellow by Piet Mondrian. So adding simple rectangles with varied constraints and randomness can help us generate Piet Mondrian style art pieces, along with some sort of granular effect, which we can add after later on using our noise functions. But for this presentation, if you have to see an example which uses simple rectangles and randomness, we can achieve this piece of art with like 13 or 14 lines of code. So here we're moving from top to the bottom on the canvas. And what we're doing here is like at each level, we are just like selecting a random point inside the canvas's width and drawing a rectangle from the beginning to that point, as well as to the end of the width from that specific point. And to add a color, we are just like randomly choosing a value between 0 and 255, which is going to give us a color range between white and black. So the entire canvas will be having color range of black and white tint. And if you are working with different color palettes, you can also change the color palette. You can add a color palette and update uh, the fill with those color palettes. And interpolating values is something we have seen a lot in the creation of generative art. As a result, this function computes a number between two integers. And the last parameter, which is the AMT parameter, is like the amount we want to interpolate between the 2 points, where like 0 0.0 will be the first point, 0 point will be very extremely close to the first point, and in the midway we'll have 0 0.5 and so on. In processing, we have a function called the lerp function, which is useful for generating dotted lines and simulating your motion along a straight line. So we can create our own lerp function as well. We can just like simply pass on the start, stop, and amount parameters, and we can just return the sum of the product of start values and the uh, one minus amount parameters and the product of the end and amount parameters. So that's gonna interpolate your values between 0 and 1. And adding a gradient fill inside a rectangle shape could be a simple example to understand how linear interpolation works. So here we are going to like add an initial color and a final color, which we will be interpolating between. So there's an easy to use function called lerp color in processing that we're using here. You can see it on line number 13. So we're traveling from left to right on the canvas, and on line number 11, we are adding a linear int variable that maps the values of index I, which is in the range of between 0 to width, and we're mapping it to 0 and 1 because we want the lerp value to be extremely small, and which is like similar to your noise function, which you'll be seeing in a bit. And following that, we will see like we have a linear int color, which is based on the lerp color function, and it accepts the colors a beginning value, the final value, and the linear int value. So after that, we will be simply use the color to fill the rectangle, and the output will be a gradient fill in the canvas. And similarly, if you are working with shapes and linear interpolation, this is an art piece called Chroma, which I created using linear interpolation, randomness, and shapes. And this is heavily inspired by the works of Felipe Pentone. We have been talking about noise. So if you go back in the 80s, while working with the first Tron film, Ken Perlin created this noise function which he utilized to produce procedural textures for computer-generated artifacts. So unlike a random function which we have seen before, which creates a number between two numbers, but the values has no link to the previous number and show no discernible pattern. But like when we are working with a Perlin noise function, noise value, the values generated do has a relationship to the previous number created because the numbers created are a naturally ordered succession of pseudo random numbers, and it appears quite organic in nature. So if you see, I've placed a lot of points, and when connecting, they form a very smooth curves on the screen. And if you try to interpolate them, this also looks pretty much smooth. To implement a noise function, we just have to initialize a noise function which returns the Perlin noise at a specific coordinate, and it can compute your 1D, 2D, and 3D noise depending on the number of coordinates you are giving. And the resulting value will be always between 0 and 1, where X, Y, Z are the number in which the coordinate is working in the noise space. You can also like set your noise seed, which is like every time you are running your function, maybe you want your random values to output the same values. So you're gonna set the noise seed, and by default noise function produces different results. So it's gonna set a constant value to the noise functions. And you can also like create a noise detail, which is going to take your number of octaves you're going to create and your fall off factor. And if you can see in this example to like understand noise in a better way, like this procedure will generate an output of random points which resembles a cloudy textures. But when you'll see, like these are just like random points on the screen. So here we are moving from top to bottom, like we're covering each single point on the canvas, and at each index we will see like there is a noise value which is taking the x offset and the y offset values, and the noise value is between 0 and 1. But we want a color value to be in the range 0 to 255, so we're just like multiplying it by 255 to get a color range to maintain this RGB index. And then we just like once we get this shade of color, we just gonna add the color to the pixel and then increment the x and y offset. So we will see like when we run the program, we will get this clouded structure by just using points. But the as we're using noise values, the RGB index values are very close to their predecessor. But if you don't use the noise value, and if you had used just a random value, the output would have been a very granular effect instead of a very smooth one. We also see like we use a very mix of noise values and mathematical functions like trigonometry. So in this example, we can see like how we can work with noise and sine and cosine waves to generate this piece of art. So what we're doing is because we want the points to be aligned in a circular way, we are running a loop, while loop between 0 and 2 pi, and the sine and cosine values are between 0 and 10. So they are mapped very closely to the x and y offset. We are then building a noise factor by mapping it to a number between 100 and 150 from 0 to 1 in order to spread out throughout the canvas. And we're also using a z offset because we don't want our curves to travel in a very same direction. So once we have these x and y coordinates, we can simply feed these coordinates into the curve vertex, which is going to create these curves. And once we are just like out of the loop, we just decrement our z offset and the radius so that the new wave generated has a smaller radius, and until the draw function is executed or it converges to something. We can also work around with tweaking the RGB values to add multicolors and different opacities as well. And the output will be very discernible and will be very different each time you're running the loop. And we see like it's very important to like add moments to your art pieces because it uses Berlin noise functions to generate noise values, and these noise values can be mapped to Berlin noise fields, which is going to, and we can further add some granular effects, as you can see in this piece of art, which is using the noise points and randomness along. And these are like two dimensional fields of vectors, and each pointing in the same but an opposite direction as its neighboring vector. And as we are adding some sort of a movement, we are updating their velocities, uh, which are influenced by the vectors themselves, like the previous vector and the next vector. And we can also use mathematical factors like trigonometry, and we can render those particles using animations, and we can see some very cool effects. If you see on the left hand side, this if you just let the loop run, you'll see all these curves moving. And simplex noise has which is like it's like similar to your Perlin noise but has like higher dimensions, and we can like further generate n-dimensional noise functions in this. Like in typical implementations, the four processes are coordinating like skewing, simplifical subdivisions like gradient selections and kernel summations. So together they can just like add a movement to your art piece. So if you have to see an example which includes your movement, we can see this live example of how noise fields work by adding movement to the art piece, where particles are having a very smooth transitional movement from right hand side of the canvas to the left hand side. So to generate this, we first like generate vector points on the canvas by adding p vector points, which is a processing function. And we just like initialize a points array. We just append those values in that point array. Once we have that, we'll be like looping over the length of the points array in the draw method, which is going to take the values one by one and saving them in our vector object. Then we're going to execute a nested loop, which is going to run from 0 to 20. It can be anything from 0 to 50 or so. And we then map the values of the noise function between 0 and 2 pi. And each iteration, we're doing this because we are obtaining radian values, because this function initially gives us the radian values and we have to map them. And if you see the x2 and y2 parameters, they are formed using the noise values, which takes the sine and cosine waves. And we then just like update these values further because we want the following points to have slightly different directions than the previous ones. As you can see, we are flowing from the right hand side to the left hand side. But the thing is, like, we don't want them to have a very completely different direction to the previous one. So that's why we're using noise. So eventually they will have a different direction, but very similar to the last one. And once we kept it running for some time, we will have these Berlin noise fields made on the canvas. We also make use of a lot of geometrical and fractals and chaotic systems when working with generative art. And this is like the one of the very simplest example, and this is called Sierpinski Gasket, and it's like a well-known example of geometric pattern. So what we do is like we recursively split the triangle and produce smaller triangles inside it. And if you're just like working with curve vertex and Bezier curves, we can just like update the Sierpinski gasket and uh, add some fancy movements to it. This also brings to the fractal systems like the recursive approach we follow, and which further takes us to the Mandelbrot set. So, the Mandelbrot set is something very fascinating because the more you go inside, the more you zoom in inside a Mandelbrot set, you will see more similar patterns uh, emerging through it. So as a result, it is shown like on a complex plane using a coordinate system based on complex number, which you can see like z equals to x plus yi iota. And as a result, we select a point in the coordinate plane and send it to the equation, which iterates n times and creates your fractal systems. And in a similar way, how Mandelbrot set works, we have created Julia sets, which are quite close to Mandelbrot sets. And these are the lines that separate points that tends to the infinity uh, from those that don't. So it is a part of the Mandelbrot set itself. And we can see like whenever we're working with a Mandelbrot set, it's going outwards and forming this bifurcation diagram. And if we dig deeper into this bifurcation diagram, we will see it is showing a very chaotic pattern called a logistic map. And because we are using only real values in our equation, and this bifurcation diagram only exists on the real line. So this approach was used initially to generate random numbers, and it gave rise to the concept of a chaotic behavior, and which further is called chaotic theory, which means like the small change in the initial state can result in a very drastic change in the final outcome. Let's say we modify the beginning state by a small amount and we believe the end outcome will be somewhat changed as well. However, we are left with a deterministic chaos. As you can see, for examples, these are all of the same program. So the first on the top, on the bottom left, we see a very small fractal which eventually takes place of the one we can see on the right hand side. Further, we see attractors being forming from these chaotic systems. So these attractors are like mathematical systems that are represented by coordinates and tends to change over time. And similarly, a majority of these generative art forms we generate are chaotic in nature. For example, if we just like modify the A, B, C, D parameters slightly in the De Hong attractor, we see like the attractor generated is completely different from this one. And if you're not doing any processing, you may also use, there is a very good library for creating attractors called PyViz, which makes use of data shaders. And there are some other attractors as well, like Schwesen attractors, bedhead, and forth. So you can play around these attractors, which works around the principle of chaos theory. But whenever we are working with art forms, we see they require a lot of colors and paint. So we can also simulate these effects in processing in Python. So how we can do is like, to give you a very broad idea, we start with a polygon and start expanding its edges outwards, doing so by recursive process. And by running it through a deformation approach, we are finally going to obtain really fine features on the outside section, as so shown in the second image. So the first image is like somewhere in the between, where we have just like expanded the edges of the single polygon. And to add more, you can add some further blur effects and work on pixels, overlay effects, and pixel sorting. So to see this in action, we can say like we can begin with a polygon with say 20 sides and attach those values to a polygon object. We can see on line number uh, 11. And then we have set a midpoint value of 50. This can be anything. I'm just like working on a smaller value so that it doesn't take a lot of computation. And then we attempt to like split the sides, and as a result we call the get mid function, which is done by supplying the polygon sides, the polygon object, and the mid variable as inputs. And we gave like two numbers as the mean and standard deviation to the get mid function. And we're looping around this polygon object, as you can see, which is taking a prior value and a current value, and then we are finding a midway between them by sending the data to get center point, which produces a random integer that fits the Gaussian distribution. And we are then adding the previous value generated to this new midpoint value each time to a new vector object, and hence we get the value. So each time we're getting so many different points on the vector space and so many polygons, and we are just like deforming them together to fit the Gaussian distribution. So now what I'm doing is like I'm looping from 0 to the updated polygon object length and creating a variable that takes the value at j index of the polygon object and passes it to a random Gaussian function, which produces a random integer fitting Gaussian distribution of all the points you're passing. And then we just like create a vertex at those spots and get the x and y index. And as a result, we will soon have thousands of vertices, and we will be able to deform the basic polygon with 20 sides into a proper paint like effect. And this is the random Gaussian methods for the same function. And if we let the function run for some amount of time, it's going to take little time, and we're going to see this deformed polygon, which can be used to simulate paint effects. Similarly, some examples can be seen here where I'm using a similar approach to generate such art pieces, which is not just using a simple deformation techniques, but it's working on the same principle. To end the presentation, I'm just gonna go over how pixel sorting algorithms are working. So pixel sorting is a process of separating the horizontal or vertical lines of pixels in a picture, and then we are just categorizing the locations according to a variety of factors. And if we see the working, we just like load the pixels one by one. For this, we can make use of an accessor function, which chooses the original pixel location, the position of the pixel, and then we just like select the next pixel location. Then we adjust the signs to observe how we are changing the directions. We then compare it and swap the pixels based on some sort of factors. It could be anything like a brightness or any other criteria. And this is an implementation for the same, but like due to this like time allotted, this is going to take a lot of time. Won't be going deep into this, but you can just like go over the comments and add it inside the program because they are self-suffice. And if you just like let the program run for some amount of time, you can see like the top image have been converted into the bottom right image. And if you just like work with another different type of images, add some different criteria, you will see you will have some very different unique looking pixel sorting algorithms, which will be deforming your images into completely different art pieces. And on that note, I'm going to conclude the presentation, and thank you so much for joining in. Uh, I'll be sharing the code files in this presentation on Hubilo, so you can just like go over there and work around the code on your systems using processing. And if you have any questions, you can hit me up on Hubilo or contact me on Twitter. Thank you.
Thank you, Neeraj. That was an amazing talks from you. So we have some question from the audience. So the
Mhm.
first one is from Yahya Fadullah Al-Fatih. So he asked, are you making some NFT art with it? Because yeah, it,
Definitely. If you see platforms like art blocks, which are like specifically focusing on generative art, you can definitely make NFTs out of this, because every time you're running the function, the entire program, you're going to yield something different. But to make it unique as an NFT, you set your seed values as a noise seed value, as I mentioned in the talk. You can use that specific noise seed value, and that's gonna be a license for your NFT.
oh, so it's possible to create it.
Definitely,
A lot of
definitely, yes.
people try to
Uh,
use it, right?
yes, yes, yes. If you just like head over to art blocks, you will see Fidenza, which gains a lot of popularity by Tyler Hobbs, and then Skyscapes by Matt Deloy. So you will
Oh,
see like generative art has been used a lot in the NFT space.
oh, cool. That's amazing. So the next is from Kamal Kurniawan. So the generation process seems to rely on random noise a lot. So is it possible to generate without random, or does the noise distribution matter? Example, is it uniform or Gaussian or anything?
Uh, so uh, so when I said, like, when I talked about how what is generative art, I said, like, if you don't use an autonomous system, if you don't have some sort of a randomness, if you're not including the machine to be a part of this creative process, then it's not going to be a generative art. It's more of a digital art, because you're just like specifying some specific endpoints, and the machine is going to create that. So in this iterative process, some sort of randomness is used, so that the outcome is not completely relying on what we are telling the system. We are also making use of the creative power of the machines as well. And the distribution doesn't matter, it could be anything. It's up to you. As in the deformation techniques, I was using a Gaussian distribution. You can also work around uniform distributions as well.
Okay, cool. So the randomness is what makes it more generative.
Yeah, that's why we always have this specific noise seed value, so that we have a value mapped over somewhere, so that if you want the exact same piece again, we can just like use that specific noise seed, which is going to generate the same art piece again, as we see in NFTs as well.
Okay, so the next question from the same person. So chaos theory somehow reminds me of Conway's Game of Life. Are you
Yeah,
aware of it?
yeah,
Yeah.
definitely. So Conway's Game of Life, this automata theory. So yes, it works on the principles of chaos theory. And if you see, a lot of these art forms have been created with, not specifically on Conway's Game of Life of automata theory, but like on something on the principle of these. So yes, definitely you can create art pieces based on this automata theory and all.
Okay. So the next one is I think this is the same with it. So is there any platform to show off this kind of artworks? Maybe beside the NFT, right? Because NFT has its
Mhm.
own store.
So usually artists have been using their own websites. Most of them are showcasing these on Instagram, but there was a platform called, I'm not sure exactly the name, but it gained some sort of popularity. It's called New Art or something. But like there hasn't been any specific platform apart from NFTs, because generative art, or all kind of AI art, or computational creative products are in the infancy stage. We don't People don't understand these properly. But with the coming of NFTs, it has gained some sort of attraction. And in the coming years, maybe new platforms will be coming up, which are specifically focused on art pieces created using generative processes as well.
Okay. So and then there's other question. I think this is so long. So it is interesting that you use processing. I once used it for modeling a robotic simulation, but the stable Python model was based on Jython, which is still Python 2.x. I wonder what version you use, and there are any drawbacks from you using it.
Oh, so I'm working with the Python 3.6, because they have this this entire process, this entire port, or the migration of the product, this Python mode, was a part of GSOC project in, I think, 2015 or 2016. So they have been constantly updating this process, like the entire library in Python. So yeah, if you are working with the latest version of Python, you won't be having any kind of issues.
Okay, cool. So just the latest Python then, and then I think this is the same with you. So is there any art exhibition presenting artworks generated by the neural networks?
Yes. So there's another talk I gave, which was specifically focused on neural nets and machine learning in computation processes at PyCon APAC. So if you have, you can head over there. And maybe whenever they release that, you can just like completely understand those. But like if you see the works of Mario Klingemann, he's like one of the pioneers in um, art pieces created using neural nets and all. So there have been small exhibitions happening worldwide, where people are just like showcasing their art pieces created using neural networks and um, other machine learning techniques, RNNs and all. But like it's not happening at a larger scale. But like again, with the coming of NFTs, we are seeing like some very tremendous amount of exhibitions which are completely focused on these art forms. But like if you want, you can just like see the works of Mario Klinchman, Hella Serene. So they are working with a lot of these art pieces, and their works have been exhibited at a lot of art exhibitions as well. And in 2019, as Christie's auctions, the first painting was also sold for a couple of, I think, to $50,000 or something around that. So it's in the infancy stage, and with the coming years, we'll see more of that.
Okay, I think that's all the question from the people. So thank you, Neeraj.
If
It's really a great presentation because
mm,
it's a new thing for PyCon ID because we a lot of us only talks about machine learning, the web framework, the data, and then here's come you to talk about art because it's really new. So for you guys, don't worry, the session will be recorded and you can watch it again in View below for the next 30 days. And so for you guys, please give the words to the speakers. So you can go to pycon.id. Thank you, speakers. We will forward the word from you to our speakers. So that's it. Maybe Neeraj, you have any other comments?
just one more thing, like how can I just give them the link to the code files so that they can work out those examples I've shown in the presentation?
Oh, sure. You can call Budi in our Discord channel and he will forward it to our attendees.
Okay, perfect.
So
Thank you so much.
thank you so much for Neeraj. See you